Okay, so last time we added the addition and subtraction to our custom integer class. Today we will continue with multiplication and division. So we open our big int and since the last demonstration was done by Mr. Carlson, maybe this time Mr. Stöckel would like to show us his solution. Yeah. Oh, that's new, interesting. Probably 3, but I don't remember for sure. Mm-hmm. It doesn't matter, that's more or less everything the same. As long as it works, it works. Mm-hmm. Yes. Mm-hmm. A VNC viewer. Okay, in this case, let's quickly check that. So, to get the IP address. Where's the chat window? Chat window, here we have it. So IP should be, I think, this one, and the password should be unchanged. I think it's this one. Let me try it out. That's the wrong IP address. Or is that completely broken? That would be annoying. It looks like that. Yeah, that's broken. One moment, please. I need to restart something. That looks better. Still doesn't work. that must have broken, like, it worked, it still worked yesterday, so it's a new issue. Okay. I just reboot the whole machine. It's thinking. Okay. Okay, now that's the right IP address. 5100. No, wait. No. That's the copy. The copy and paste failed. Like when copying and pasting from a virtual machine over a remote desktop connection, that sometimes the clipboard synchronization copy and paste doesn't work at all. Okay, let's just type it down. Yeah. 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 And yeah. Okay, this one should be the right one. And if it doesn't work, then just give it time and try again, because at least the the number for the port is wrong. Oops. 5100. That's the right port number. It's annoying. Okay. Different approach. Oh wait, this is also not right. 0 is the right one. Okay, now it should have the right AB. Let's see. Try the first IP address again. Yeah. I guess this one. Maybe like this. Perhaps. Okay. Mm-hmm. Mm-hmm. Yes, this is simpler. Mm-hmm. I think it's defined with using a function. Just take a look and then we will know. Yeah, it's defined using a function called multiply. And the function called multiply is defined, it's so the operator is in line 103 and the function is in line 99. So basically, ideally, it take just the function, remove the return begin 0, and implement the function so that we can have this nice way it's looking. And the way you could put everything in the header, but it's nicer to make it in the CPP file. So here, just comment out the whole thing. Just make a semicolon. Yeah, and then a semicolon. Yeah, and now you can implement the multiply function in the CPP file. Yeah. Mm-hmm. 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 Okay. Mm-hmm. Mm-hmm. And this works. First, let's try out whether multiplication really works reliably. One step after the other. This we can undo. Mm-hmm. Which line? Because the loop runs for a very long time. Mm-hmm. Just until line 63, including line 63. The rest This will also take some time. Just put the other comment there. You can print the number using this print method we used here by casting to a 64-bit integer. What's res? It doesn't know how to cast res. You need to use the big int2 int64 function. How did we break here? Apparently you're writing somewhere you are not allowed to. You can press on wiederholen and repeat. Then it brings you to where the crash was, and it seems it doesn't tell us which one. So in one of these two numbers, or maybe in the result, in the result probably, you have written past the allowed index, and the way the allocator when running in debug mode works is that it will, after the memory it gave you, it will actually allocate a bit more memory and then put after the range you're allowed to use a defined pattern that it knows, and depending on details it might either be made such that the pattern is just always the same, or it might be like really a generated random number that it remembered somewhere, so that it is very unlikely that this pattern would then on its own appear anywhere. So if you write after too much, if you write past the memory offset you are allowed to use, and then you deallocate the memory, it will check whether this guard area was intact, and if it was not intact, it will throw an exception like this, indicating that you wrote too much. So I assume that what's wrong here is that the size in the result integer is that you did not allocate enough memory, or that you accessed too much of the data. The annoying thing is that here it triggers from the destructor, which is called implicitly by the compiler, so we don't know which variable it was, but since we only write to the res variable, we can assume that that's where the error originated with, because you are not modifying the two input parameters. Also, if you would even read past the allowed offset from the input parameters, it would either crash instantly when you just run into some invalid memory, or the guard page would not, well, the guard region would not care, because you can read it. It only triggers if you change it. So let's see, you allocate size, result size is the size of the two. Then you have R size. Nope. You have the case is less than or carry. So if carry is set, it will go one further. Then you need to add result size sum plus 1 to be always on the same side in line 250. Also, realistically, this would not be the best approach, because now if you, let's say you have a loop in which you are multiplying a lot of numbers. If you always make +1, with disregard to how many bits of the number are actually in use, you will like grow your number with every multiplication by one chunk. So once this works, the next improvement step would be like to check whether in L size and R size the highest order chunk is 0, and only if in both it is not 0, then add the +1, else not do the +1. So that you only increase if you expect that you will need it, and not in any other case. But first, just to check whether the mechanism works, we can do it like this and just let it grow for now. Then I would but we will call stack. Oops, call stack. It's the distractor, but it must be this. First, for testing, just make +10, just to see whether then it's fine. That's experimental programming. That's not always the best thing, but sometimes if you just want to quickly test. Okay, so why is this wrong? Because we take the size of j and then the size of I, and we multiply and we add them together, and that's where we access it. If we make this +1, okay, but then it just maybe for some reason means that you get into the carry case more than once. So you could put a breakpoint on the loop in line 259 and step through it and check how often you trigger the case that carry is not null, not 0. Okay, so you trigger it twice already. You can make conditional breakpoints, yes. Okay, so well, at some point it must, because if you make it +10, it didn't. If it would always be unequal to 0, then the loop would run forever, which it does not do. So there must be a case where it is. Sorry. You asked whether it's not equal to 0. Yes. That's why I asked earlier. Are you sure this is working? So you are sorry. In line 262, you have the t-chunk product, which is the the result of your operation, and this is the size of chunk, right? So then you assign a chunk to the other chunk, and then you are moving your product, shifting your product to the right in line 264 by its size. So you always are shifting out its entire content, and it always will be empty. So this is not the right way to get a carry result. If you want carry to work, it would necessitate that your product variable is at least twice as large, uses at least twice as large a type as chunk itself, which given that we want chunk to be even 64-bit, will not work because we cannot have it anything bigger. So you need to figure out a way to so one option how I guess this could be made working would be if you would check how many bits your chunk has, and then kind of divide the chunk into two sub chunks and make all your operations on this on these sub chunks, which are just half as big as a normal chunk. And then you would have enough data to do the shift. But yes, so basically you would still allocate a product chunk as chunk, but for R chunk and L chunk plus the whole rest, you would make like half chunk variables of type chunk itself, and then use bit operations to fill it only with half of the data, and then you would do it twice, for the first half and then for the second half. That will be a significant rework of the whole thing. It will not be easy. You must have used numbers which did not result in the carry being used. Yeah. Okay, so what do we do now? Do you think you can make it work within an hour's time, or? Okay. Then maybe someone else would like to provide their hopefully working solution. Maybe Mr. Hotel. Okay. Well, then it's up to me to make it work. Let's see. So what do you what would you prefer to see? Do you want to prefer to see the A correct? Because there is like not one, but there's certainly many, but A correct solution to the multiplication, or do you want to see me trying to fix this approach? To be honest, I'm not sure that it would actually work fixing it. No, it should. Because if you, in the worst case of an overflow, realistically you only overflow by 1 bit, so splitting everything in two halves should work just fine. Okay. Okay. Okay, so we just comment this. Oops. We just comment this out. Make a new multiply function. Right. So we have our 6 int. We call that product. Oops, is equal 0. So we start with an empty thingy. Okay. Okay, so we call this the multiplier. Okay. You have a product. So while no, this would not work this way. My approach is destructive. Multiplier, we need copies of everything. Multiplier. Make copies of everything. This I will move here, that looks nicer. Okay. So while multiplier is not 0. If multiplier and 1 are not 0. So here we check whether there is any bit in multiplier set. Here we only check if the rightmost bit is set. And if the rightmost bit is set, then product is equals plus multiplicand. And then multiplier is equals multiplier 1. Huh? Oh, wait. That was supposed to be a plus, yes. Thank you. And is also same thing, just in that direction. Actually, we could even make this, since it's always the same variable, we could also write it like this: equals shift, wait, shift equals. Did we implement those? Oh, we did not implement. I think we did not implement those operators. So let's just leave it in this version. Okay, and return product. And that should be it. Let's try it out. Now the limitation of my approach is that it behaves the same way the computer itself with a real machine type would behave. So if you multiply two numbers which don't fit into the result size, oh, I didn't say the result size, then it will just cut off the excess. No, but that should actually, no, it should not, because we are always using the plus, and the plus, will the plus actually, how did we implement the plus? Will that increase it or will it cut it off? We have the add function here and add the count. Wait, where do we allocate size? Max. We take the larger of the two. This will be reasonably fine. Let's just try it if it works. If not, then we need to tweak the like pre-grow the thingy before we use it. So we have two numbers, we multiply them. Right, product is this, and then we can also make the what it should be. So the end line we don't take. Product is this, and it should be doesn't need to be 3 letters. This asterisk this, right? 1 times 2. Okay, the order doesn't matter, should be, yeah, okay, and let's put return here. So we don't print too much. Well, it works perfectly. It does what it's supposed to do. I'll just shift it by 1, 2, 3, 4, 5, 6 characters to make it easier in comparison. 1, 2, 3, 4, 5, 6. No, that was 1 too much. Yep, perfect. Okay, so that's my solution for the multiplication, and it should be reasonably fast. So it's not like if you have a number, we will just run the number and make plus and plus and plus all the time, but we really just go through the thing. So the loop runs up to however many bits the multiplier has, and actually if the multiplier is a smaller number, which is often the case in many operations, then it will terminate prematurely, because it will not like compare ad infinitum until the end of time, but instead it will just break out. So if you have some normal code where you just multiply by 2 or by 10 or by something, then it will, even if what you are multiplying is actually a significantly bigger number, then the thing will of course break out at the right moment, so it will not do empty operations. Of course, this is contingent on the user of the code then picking the right order of what to multiply with what. But this should be good enough for most cases. Okay, now for the division. Right. So for the division, we have those two functions. And the way I implemented it, we are using a... Oh wait, there is something... Something was edited here, I think. Was it? Yeah, there was something. Yeah, there was something removed here. We need that. Okay. Or maybe before we do that, my division version, maybe someone else would want to. I'm sorry. I think Mr. Otelli, you don't have a solution for division either, right? Okay. Okay, we can do that. We can do it this time. I will be just very fast with my division thingy. Because it's also a work smart and not work hard sort of solution. Okay, so what we do is we implement a helper function. Oops. Stupid typos. Using static in a C or CPP file, what it does is that a function which is defined this way is only visible in the scope of the file. So normally, if you have a function somewhere in your C code and then are linking stuff together, you could throw the definition of the function into any other CPP file and then you could access this function. But if you define it as static, then you cannot do that. Then any other file than the file in which a function is will not be able to link with this function, even if it has the definition. The advantage of doing it is that you can use names which you don't need to care for them being unique, because if you would have two CPP files with functions with the same names and they're not static, even if they are different to some extent, and you don't like have put the definitions into any other files, the linker would still bug out with that this symbol is already defined. But if it's static, then it knows it's only within this scope, so they will not conflict with each other. Okay, we'll call it long division, and it takes a couple of numbers. So a const begint reference n. That's our number. Then our divisor d. Then it's no longer const. This will be the q, and the r. Okay. And before we look in the function, let's look how we want to use it. So first of all, in divide, if we check if this is, so if this is 0, then we need to bug out. I decided just return -1, which assuming we have unsigned integers, as we do, is the max value, which kinda is the closest thing to infinity that we can have, so it's within reason to do that. If, for example, the floating point representation of numbers has reserved value patterns for, I think, infinite and for a few other special cases. But integer don't have anything like this. An integer just goes from min value to max value, and there are no special values anywhere. So we need to make it work with what we have. Then we use our function, so as begin we define q and r on long division asterisk this asterisk hotel comma q comma r and return q. And for modulo, it's kinda very similar, so we just copy this, we just return r. So the way the function the long division works is it does both for us, and returns both values, so we can then pick which one we are interested in. Okay, so q punct oh wait, we did not. It might be annoying. Let's define the function on our thingy so that we can access the private thingies, but here we will put it here that it's protected so that you cannot access it from the outside world. q.alloc data. Oops. This says size, and it's size n. Chunk count. Row size. I think row size is the right one. How do we feed alloc data? Yeah, we use size, then it's the right one. Then we do the same for r, so that we have enough room to work with. Now we need a loop for size t e is equals n. I need a count of bits. We don't have the bit count. So let's take chunk count times of the chunk small h times 8. This gives us the total count of bits. Not quite. We want this to be smaller by 1. I is greater equals small I is greater equals wait. That's annoying. And then this needs to be signed. Okay, let's go with it. Why is this complaining? Oh, chunk count is a helper function. Okay. Then we just take chunk count. Oh wait, we can. That's better. We can just take get row size times 8. That gives us what we want. Right. Semicolon I minus minus. So r is equals r, but shifted by 1. R punct. Do we have set bit at 0, comma n get bit at I. Okay, and if r is greater equals d, then r is equals r minus d. Q set bit at I, comma 1. Set bit at I, comma 1, and that should be it. Yeah. Needs to be defined as const. Otherwise, the other function is complaining. Here it was complaining. Okie dokie. We are working with shots. That should be enough work. Main. So, oops. Let's roll. It's an unexpected result, but it's the right result, so it works. Okay, and now what we also can do is, if we want to be particularly efficient, there are special cases where we don't need to do the whole division or the whole modulo. That actually that would also apply to the multiplication case. So we can move this into a helper function, although it doesn't matter. Let's keep it where it is. Now let's move it into a helper function. Multiplicand, comma. Wait, I missed one. This one. Multiplier, multiplicand, and product is comes out as a by reference, also const, just in case. That's wait, not quite. No, quite enough. Product we zero it to be 0, then we do our thing, and then here we call lang lang multiplier with order, comma, asterisk this, comma, should have kept one of the definitions, product. Right, so we have the same nice pattern that we use with the other one, and first optimization of course is that if other is 0, then just return 0, because then we don't need to do anything, we know the result. But let's come to the optimization. So if you bit shift to the left by 1, that's like multiply by 2. If you bit shift to the left by 2, that's like multiply by 4. If you bit shift to the left by 3, it's like multiply by 8, then by 16, and so on and so on and so on. So we could try to find out if instead of, and with division is the same, if you shift to the right by 1, it's divide by 2. If you shift by 2, it's divide by 4. If you shift by 3, it's divide by 8, and so on. So in very special cases, you can bypass the whole computationally intensive multiplication or division operation by using a trivial bit shift. And I think, if I'm thinking right, we can do that quite easily, or at least easy enough so that it will be worth as an optimization. So if other, oops, wait, not too many, other and other minus 1 is equal 0. So if this, what are we missing? Are we missing an operator? Or are we missing a bracket open, close? That should be right. Expression must have bold type, but wait. Here is one bracket missing. Okay. Right. So we can take a look later in why this works, but it works. Basically, if this is true, this if, then the other is of a type that of a content which will allow us to do the shift trick. But then we of course need to still to figure out to shift by how much. So int pause is equal 0. We start with 0. For need a copy. Is equals other minus 1. Actually, that should just work fine if we do it like this. Temp is equal 0, comma temp, shift. Oh, I don't think we have this operator, do we? Plus. We don't have this operator. Is equals shift 1, plus, and it doesn't have a body. So this will just loop through the thing and count up until we find a place where there are no more ones set. And it technically in the whole thing should only be one which is set, otherwise the whole scheme would fail. So we just return the shift operator, shift left. Right, we're on our current version, shift left by position. And this does the multiplication. It should be more efficient, although this is also quite efficient. We could look into making this this search loop more efficient. And with the divide and modulo, we can do it similarly, so we can copy our this one, this will always be the same. Oops. Okay, and for divide, we will just do the shift in the opposite direction. So let's grab the whole code here. This is the same. We just make shift right. And for the division, we also need. Do we wait for the division? For the division. Sorry, the modular is even simpler. The modular will be. Do we have end? We don't have end. But we can use end. So tone asterisk this and other -1. This should give us, for the cases where this triggers, the same result. And in this case, it's like obviously extremely fast. This search loop it could be made better, because now it's like it's shifting the thing. But what we should do is just we should check within it and then shift our position. That is not a performance solution which I made here, but was the fastest thing I came up with. Of course, now we need to find a number which will work with this. So let's go with I don't know, 128, for example. That is a number which should have only one bit set. $128 has only one bit set, as you see here, so that should work fine. Let's run it. So for division, division was we tested, it worked just fine. And now let's try also the multiplication. Oh, that should say is divide. Okay, for multiplication it should work as well, and it does. And we can of course test whether it actually does what we expect it to do. We just go to begin divide here, zack, to see whether we're actually entering our code. And as you see, this code is detecting the one bit being set correctly. Yeah, we can of course check whether it is still valid if we go back to something else. So if we are here, then it should not trigger, and as you see it doesn't trigger. We just go into the slow path. We don't need to test this. This was shown to work already. And let's see if we can see how this works. So main. So let's start with the 128. Then let's copy this code here so that we can not forget what we were looking at. Add some more space. So 1 to 8 is equivalent to 1 0 0 0 1 2 3 4, and equivalent. Right, and 1 to 8 minus 1 is equivalent to 0 1 1 1 1. Sorry, not much. 1 2 3 4. Right. Maybe we should make it like this. That's nice. Okay. And now if we end them, then the result should be 0. Now let's take any other number. Let's take 1 2 3. My preferred dummy number. 1 2 3 is this. And if we then make minus 1, then we get that pattern. 1 2 3 minus 1 gives us this pattern. Wait, it didn't copy. Gives us this pattern, and now if we add those together, you see that there are actually quite many ones which remain, so the result is not 0. And in fact, this should be true for any number we can think of. So I could make a loop now and just run it from 0 to 225, and we would see the same behavior, which actually we could do. Let's do it. For int e is equal, oops, int e is equal 0 slash e is less than 255 and 256. Let's go for the whole range. I plus plus and oops, not the right brackets. Right, we take our if. E and f percent e is a 2 backslash n breakpoint, and let's see if the result is what seems reasonable. Oh, it helps to actually specify the argument. And now it's complaining for some reason, which should not be complaining. Well, 0 is valid. 1, 2, 4, 8, 16, 32, 64, and 128, and this is correct. If we would have run our loop one number longer, we would also see 256, and so on and so on. But as you see, this trick here is reliable. I mean, we can also go to actually, why not? Let's go to int max. No, let's not do size t. Let's do unsigned int to 0x1 2 3 4 5 6 7 8, and let's include the last value. No, we cannot. If we include the last value and then we do plus plus, then it will wrap around back to 0, and then we will do the whole thing. We need to keep this must be less, because the last value will be this and then it will bug out, so we will not print the last result, but this is good enough. And it should be fast enough as well. As you see, the last ones took a second longer, and this one kind of is negative. Wait, let's make this print unsigned values. Yeah. Then it works fine. And to however much I can see it by eye, it is kind of correct up to here. The rest I don't really remember by heart, but this I can attest that they are all valid, and I assume that they must also be valid because it's kind of plausible also the increment in which this grows, and that is like the one after max int signed. That's why it was negative, because it was already the first value that wraps around to the negative side of the value range if we would have used a signed integer. Right, so we only have 25 minutes left. Let's take a look on the string size, if string homeworks, if there's anything that we could do already today. That looks like it can be demonstrated in half an hour. Xstring, no, that's the wrong view. Xstring h. What do we have? The homeworks. So homework. Yeah, that sounds like it will not take too much time. So Mr. Hotel, would you like to demonstrate us your implementation of the compare function? Then the 80.108 and so on and so on. I will have to find out why my second router is not routing properly, because yesterday it was still working fine. And now it seems to have repaired itself. I know it did not. It didn't start the routing roll. Now it throws a recoverable error. Using Windows Server for routing is a really stupid idea. I should not have done it, but I started with that in 2005-ish, and I just stuck to it. So I just go back to the last VM snapshot, which I know was still working. Like the older Windows versions, they were kind of fine, but the newer Windows Server versions, especially with regard to the roles, which are not kind of the thing you would use Windows for, they are really bugged. So the old VPN and routing stuff and DHCP and stuff, they really broke a few things, like with the newer Windows 2022 and later. Like really badly, and I don't see them fixing it. I should test for that in 2025 server. They fixed some of it, but I just should switch it to Linux, and that's it. That would be much more responsible. For routing tasks, it's not what Windows was made for. But it's so convenient. It has a graphical UI that's so nice. You can set port redirections. I mean, if you don't take like a existing Linux installation, but one of this Hyper, what is the I don't remember the name. There are a few specialized Linux-based OSes which are really made just for routing. They work perfectly fine, like the one from MikroTik, or the other is IPFSense, I think. And the open source version OpenSense of that. So that would be probably, and it provides also a graphical interface, but then it's just a single purpose thing. The nice thing about the Windows Server is that you can have routing on it and a virtual machine host and other things and everything at once. That's why I started using it. But the last two, the second to last release, the last release I didn't test of Windows Server is really not working satisfactory with regard to this functionality. Okay. Okay. Well, you should not sort them at all. So the way this should work is you first compare lengths, and if the lengths are not the same, you just return like which one is longer. But if they are the same, then you need to compare really byte-wise the content, and when you find the first char which is not the same, then you return in which of the two strings the one char which is not the same, well, sorry, the first char which is not the same, in which of the strings it's bigger, and you ignore the rest of the string. Yeah, we can use the trinary operation. That will work just fine. While hint, you should run the for loop only in the else case. Yeah, yeah, that's or like this. That's the same result. The only thing is sometimes whether you do a return or a else, if the code is compiled with optimization, the compiler will in both cases generate the exactly same output, because it really, the modern compilers, they can reorder and reorganize the operations with a lot of flexibility. So it's not always good. I remember with Visual Studio 2000 and which was it, 15? I think it was 15. No, it was 2000, Visual Studio 2010, I think. When they like introduced the 10 would also be too late. One of the earlier Visual Studio versions, which started to introduce the 64-bit compiler support. When you compiled and had function calls in arguments of other functions, it did not execute the operations in the release build in the right order. And it was a hugely painful bug to fix, because like, your code works, it works on 32-bit. It doesn't do anything that when you change the bitness would make it break, and it works in the debug build, but if you make it release build, it crashes. And the result simply was because it was reordering the function calls in a way it shouldn't, and that way was one which caused a memory allocation which was expected to happen first not happen, and that was really annoying. And they fixed it like a couple, one or two service packs later. That was fixed and it worked fine, but until then it just needed a manual workaround, so that you just write manually first some variable assignments and then use those as arguments instead of putting them into the function call it directly. No, the annoying thing is that this could happen to anyone, because it's a normal thing to just use to call a function when from assigning arguments to another function call. You just have like a function, and then in the function you have some variable punct and a member function on that, and you call that and expect this to happen. And if the order there gets changed in a particular way, then this fails, and it's a really annoying error, because as said, it in the debug build it was fine because it's not optimized, and if you compile 32-bit it was still fine. So but I said that was like when they were starting with that, so it was not something that needed that like was a problem for a longer time, so they fixed it within a couple of months. That must have been Visual Studio 2005, because all the other ones, they was already long time into 64-bit. I could Google that, which was the first Visual Studio which supported 64-bit, but well. Okay, so you run, you compare them. Wait, but you just return 2. 2 is not a valid value. if it's equals 0, if it's not equals plus or minus 1. It should never return anything else than those three values. Mm-hmm. It cannot work. It must not work. Because the comparison operators, they rely on the values also being negative. And if they are always 0, 1 or 2, then it will always go into the positive case. But it's not difficult to fix. You just need to, because now you have found the first character in the in both strings, which is not the same. No, why 0? They are not the same. You are not allowed to return 0. You just use the trinary operator and you compare those two characters with each other. If the one is smaller than the other, then it's -1, and in the other case, it's 1. Or it's the other way around. Which case is plus or -1, we will need to find out. But no, not there. Why? Just for the result, like in line 85. I just asked the AI which was the first Visual Studio version which supported 64-bit. Yeah, the first Visual Studio version to support the x64 architecture was Visual Studio 2005. So the bug must be... Yeah, I was thinking like something about 5-ish, but then I was thinking was it 15, but it's obviously 10 years too late. So it must have been the 2005 version which had the bug. And I think it was in the first release. The Service Pack 1 release already fixed that. But obviously that is super annoying because you have something that crashes in a way which is absolutely impossible based on what you see in the code. Okay, so we were testing a lot of things. You can just put a test case at the very beginning. Or you can also put the whole main function into an if 0 and then write a known main function that doesn't do anything but the one thing you want to test. A hash and lowercase if 0. And put the rest in the new line. Click. And after the main function you need to make an end if. Hash end if. Then the whole code block will be disabled and you can have your very own main function replacing it. Yeah. Well, I would usually do it on the top, but it's actually more elegant to make it at the bottom so that you have the historic record maintained. Why I like to do it on the top, because then I don't need to scroll so much if I need to add an include or so. But in principle you could add your includes here as well. You are not forced to have the includes at the top of the file. Usually it's just fine to have them wherever you want. Except that it's ugly and not makes the code any easier to read, but functionally it's fine. With C it's really with a lot of things such that you can do it either way you do it, it will work and it will be formally correct, but it will just be terribly difficult to read for someone or for yourself if you haven't used the code for some time. So it's just really recommended, even for your own use, to adhere to standard practices to keep the code readable. I do not remember. Let's open a ASCII table. Then let's yep, the wait. Yeah, the wait. What's the character? The character, yeah. No, hex, character null, 1, 2, 3. Yeah, the uppercase are smaller than the lowercase. This window you can close. It is not relevant. And it didn't run yet because it's still sitting in the breakpoint in line 216. I guess we had a breakpoint in the disabled code, and the compiler, when it sees this, it shifts the breakpoint down to the next instruction it actually can break on. So the result then is that we get an unexpected breakpoint appearing sometimes if we have disabled large code blocks. You could just press continue on the and then it should be able to open the window and see the result what it printed to the console. True, false, true, false. That looks correct. Nice. And let's see the header file for a second. Yeah, that is working. That seems to be working as it should. Good. And since we're out of time, that will be it for today. Next time we continue with the other X-string assignments. Indeed. But you were only missing 2 times. That's not so bad anyways. You were only missing 2 times until now. So that's not a problem. If you find another way that is not using this bitwise multiplication, then you could upload it. But don't make it like run a loop and then just add and add and add, because that's the preschooler way of doing it. That doesn't count. Yeah. Okay. You're welcome. And what was the other guy? Mr. Sturkel. You could try to fix your chunk-based approach. As said, the idea. We actually have 3 minutes left, so we could take a look back to the other thing. But this is just like spitballing ideas. I haven't done it, I haven't tested it, it's just what my gut says it should be possible. It would be something that like, instead of having like a loop, here we would break this up into two instructions. So we would have a lchunk high and lchunk low. We also need a rchunk, rchunk high, rchunk low. So low is lchunk and this already gets complicated. We need a few helpers. So we need a chunk high mask and a low mask. Need a size t not really. Not really, because it just, at its core, it just doubles the amount of work that your code had to do. But because it does it, it will work properly. So shift is we have the result size. This is good. So shift is result size times 4. So basically, we just take the half amount. So size, if we remember correctly, is in bytes. So we take half of it. So shift is really like where the half of the thing starts. And now high mask and low mask, it needs to be filled up with like so the high mask is ff. So this is like for the short case. So if we would have here if we would have here like long, then it would look differently. But the goal of the code is to be universal. It might not work for character. It should. But if it doesn't, it's fine. So if you have such codes and you say, okay, like you have a lower bound for the size of your chunk, you say it says to be at least 16-bit. That is fine. But I think it will work with 8-bit as well. Right, and the low mask is this. Will be this, but we need to actually generate this. So how do we do that best? Yeah, that's the thing. If we would say that we don't allow characters, then we could then we'd know that we can fill in a full complement of characters with or ones or zeros, and it would be always fine. Because like in the so that's the short case, and if we would have the char case, it's this, and this means that we need to do things nibble wise, which complicates things. But I mean, let's just for now, since we are running out of, we are already over time. So whoever wants can leave, except for obviously Mr. Ströckel, because I guess you want to see how to do that. Right. So, but let's still try to be fast. So we will do it with a loop for size t equals 0, e is less than shift. Less than or less than and equal? No, less than should be enough. I plus plus. And now low mask would be, low mask starts as 0. Let's initialize them all to 0 first. So low mask gets a bit set and everything shifted by 1. So low mask is or equals 1, which is shifted by e into the left. So this will fill in all the places we need with ones, and high mask is just low mask shifted by shift. Okay, so we have our two masks. So now we have our high chunk and low chunk is equals okay, so low chunk is just and low mask. It's trivial. High chunk. Oh wait, we might not need the high mask at all. Let's comment it out for now. Because the high chunk is just a low chunk shifted by shift. And then we still we don't need to end it with, because there is nothing at the top to be shifted in, so that should actually be already all that's needed. And this is just the same with R. R, right. And now here what we do is right, we have this line goes up, and we need the same for R chunk. We have R chunk up there. Okay, that's fine. So we have R chunk, we have L chunk. But and this works bitwise. Then we need to change the order of things. Wait. No, we don't. No, that should be fine. We keep the order. Okay, so we have our two chunks, and then the idea would be that you kind of implement such a code. Just once for the high case and once for the low case. So let's write to do. Then and loop to the next chunk. So this basically is the idea. You are reducing your problem. Well, no, you are increasing your problem to work with smaller chunks. But then, since this operation here will always be done to a full chunk, but as you see by our mask, always half of it is empty, then we have space. So this line here, for example, would then look like this, because you only shift by half of it, and then you take the upper portion which was not influenced yet, and you can use it. So if I write more code, then I will do the assignment myself, so that's not the goal, but this should make it clear enough how it is supposed to work. Or do you have questions? Okay, then that will be, well, I think we only have one more lecture, so basically if you can make it work till the next time, that would be great. Yeah. So for the lecture, it's well, I usually check whether it actually works, and if it works, it's already 100% because it works. That is for this assignment. And if it doesn't work, I look why it doesn't work and how bad is the mistake. So like if it's like it's the right idea, just small detail was missed, and it's also fine-ish, that just gives like maybe 10% points less or so. That's not much. But if it's like, okay, that could have never worked, then it's 0 points. And of course there is a spectrum between that. And generally this applies for the homework for the Dingsbum star lecture the same way. If it works, it's fine. If it doesn't work, depends on why it doesn't work. for the exercises, the total number of points you get is well, all the homeworks plus for every assignment done during the lecture you get bonus points. So that gives you some opportunity, if not all homeworks were submitted, that you will still get, because like the 100 point, sorry, the maximum points are the amount of assignments times 100. So I don't remember how many homeworks I assigned to you, but that's like the max points you need to get a very good. And the things you do during the lecture kind of give you bonus points, which you can use to compensate for not submitted homework assignments. With the lecture, we didn't do anything during the lecture, only the lecture itself. Then you have in the assignments, usually you had like optional things of an assignment. So like the assignment is do this, and then optional you can also make it do that. And these optional things also give you bonus points, which you can use to compensate for missing or not working base assignments. And the only main difference here, because I think we also had optional assignments here with the, did we? I don't remember. But the main difference is that with the main lecture also have the final project, and the final project counts like half of the points, and the exercises count the other half of the points. Yeah, and that's that. Yeah, you're welcome. Then see you later.